Well, thank you for accommodating me later than I was supposed to be scheduled. Sorry about that. Appreciate rearranging. So the title is, well, the title is the title. I'm going to talk about how we've been doing computational fluid dynamics at Petascale with a Python code base. And the results, can you put the lights down a bit? Does that work? If the lights can go down at the... Well, no problem if not. So the results, or the test case that we'll focus on in this talk is flow over a low pressure turbine blade linear cascade. Oh well, don't, fine, it'll be okay. So the low pressure turbine is a component in a jet engine. I'll show you exactly what it is in a moment as we get into the talk. But we've been doing simulations, direct numerical simulations of flow over these low pressure turbine blades. Thank you. And in the context of these simulations, I'm going to present the technology that underpins them, so the algorithms, some discussion about the hardware platforms we run on, also scaling results, weak and strong scaling, performance up to 13.7 petaflops, double precision, which constitutes 58% of theoretical peak on 18,000 GPUs of Titan at Oak Ridge, sustained performance, comparisons with experimental results, and how we've done all of this with a code base with just over 9,000 lines of Python code that can run cross-platform, so as well as just running on NVIDIA GPUs, can also run on heterogeneous systems. So this is the motivation. I'm from the aeronautics department, so there's a sort of applications context for what we're doing. The motivation is this green aviation challenge, so a lot of people fly annually, that's well established. However, which is fantastic, but the downside is that it produces a lot of greenhouse gas emissions, which are not good for the planet. Also noise pollution has other impacts as well. And the key issue is not the amount of pollution at the moment, but the fact that the global demand for commercial aviation is increasing all of the time. Especially in countries like China, where more and more people now want to fly. These are some statistics around that. But this is really what it all boils down to, which is we're going to fly more as a global community. More and more people will fly. How can we do it whilst polluting less? Because from an environmental perspective, commercial aviation is not sustainable with the growth at the moment. So it's a challenge to address for the community. It's been identified both in the US and in the EU. There's two large projects looking specifically at reducing the environmental impact of aviation. So the NASA have their environmentally responsible aviation project, and in the EU is a project called Clean Skies. Now there's a whole bunch of ways to try and reduce the impact of aviation, the environmental impact of aviation, reducing emissions. These relate from everything to sort of how you schedule aircraft to take on and off at big airports, all the way through to what we're interested in here, which is the actual aerodynamic efficiency and aerodynamic performance of different components of the aircraft. So the landing gear is one source of noise when the aircraft are coming into land, and you can do simulations of flow in this context to try and reduce that noise. There's issues around, again, the noise generated by these slats and flaps when the aircraft are in their high lift configuration, when they're coming into land and when they take off. And there's issues around the performance of the engine in terms of increasing fuel efficiency, reducing emissions. And the low pressure turbine, the turbine blades I talked about, are a component in the engine. I'll show you in a diagram later on, that we're interested in doing simulations over so we can optimize their design and improve their efficiency. The challenge for all of these flow problems is that the geometries are complicated and the flow is typically very unsteady. So it's not just turbulent, there's unsteady aspects of the flow. And sometimes it's also compressible. And this is a significant challenge. These four factors here are a significant challenge for current generation computational fluid dynamics tools that industry use. And what we've been trying to do is develop a new generation of CFD, so computational fluid dynamics technology, that moves beyond the industry standard and allows, hopefully, industry to perform useful simulations for design in the context of these unsteady flows in the vicinity of complex geometries. And to do this, we are leveraging, or trying to leverage, a synergistic combination, really, of modern hardware platforms, and I'll define what I mean by modern hardware platforms in a moment, combined with some relatively new numerical methods called flux reconstruction schemes, which are similar in various ways to discontinuous Galerkin methods. How many people have a numerics background in the room, or is it? Okay. This talk has a mix, right, of some maths, some supercomputing, and some physics, so it will span across different aspects. So, new algorithms on modern hardware to try and create this new generation of computational fluid dynamics technology to solve these unsteady flow problems in the vicinity of complex geometries, to eventually lead to greener aircraft. This is the idea. So, what is modern hardware, in inverted commas? So, these are some pictures, becoming a little bit dated now, but we've got CPUs. Intel had this Intel Xeon Phi coprocessor, and now got KNL. AMD and NVIDIA have a range of sort of scientific computing, GPU, coprocessors, accelerators, whatever you want to call them. They all have a lot of marketing spiel associated with them, a lot of sort of buzzwords and flashing lights, and you go to supercomputing and there's all these big stands and it's fantastic. What I want to try and do in the next few slides is cut through to some of the salient characteristics that I think go across all of these platforms that are of relevance when you're thinking about using them, when you're thinking about developing software for them, algorithms that will run effectively on them. And so one important characteristic now is that there's an abundance of flops relative to memory bandwidth. I think most people in the room are probably familiar with this, but it's worth just going over it again. So abundance of flops relative to bandwidth. This is for CPUs from 1994 through to 2014. The red line on the log scale is the flops, the blue line is the bandwidth. So from an algorithmic perspective, to use this red line, you need an algorithm that fundamentally has to perform a lot of flops on a byte of data. Otherwise, it's very hard to key into the red line. And a lot of the CFD algorithms that are in use in industry today were designed back here or previously when the situation was the other way around. And people were thinking about doing the opposite, minimizing the number of flops on a piece of data. Also, that red line, the acceleration of this red line is all now driven by parallelism on the socket. But there's also obviously parallelism you can think about across sockets, and then within a socket you've got parallelism across cores, vector lanes. So an abundance of flops, and that's all driven by parallelism. And also these modern hardware platforms have quite complicated memory hierarchies. And so on the GPU there's device memory on the GPU, global memory and shared memory and register memory, and you can think about how to take advantage of all of these different types of memory if you want to. On KNL, I'm still trying to get my head around how all of the different permutations and combinations of memory that you can leverage. So that's another aspect. So abundance of flops driven by parallelism, complex memory hierarchy, which are challenges, but there's significant performance available if you can harness it, and this is just the peak double precision teraflop number for a P100, NVIDIA's latest GPU. So that's some comments on the hardware, and we're interested in using all of this modern hardware. I'll talk about our cross-platform coding paradigms in a second when I come to the software. From an algorithmic perspective, we've been interested in these flux reconstruction schemes. They're first proposed by a colleague of mine who's at NASA, Glenn, in the US in 2007. Their two most important characteristics are that they offer so-called high-order accuracy in space, which means, in theory, they offer an efficient route to high levels of accuracy if you need high levels of accuracy. And I would contend that for these unsteady flow problems I talked about at the beginning, these unsteady turbulent simulations, you need very high levels of accuracy to resolve the physics phenomena. So the high-order accuracy, which is a property of the numerical method, gives you the ability per se, notwithstanding anything about hardware platforms, to resolve these flow features. And also, these methods work on unstructured grids, which means, so a structured grid would be tessellating a volume with just cubes, of regular size, which is fine if you want to just fill a cube itself. But if you want to create a mesh around a complex landing gear, you really need an unstructured mix of tetrahedral prisms, pyramids, etc., all jumbled together. And so only certain algorithms are able to work on these unstructured grids, and flux reconstruction schemes can. So that gives you, the high order accuracy gives you an efficient route to the high accuracy that you need for the physics, and this gives you the ability to work around things like landing gear, etc., with the complex geometry, the unstructured grid part. This is a sort of schematic I've put in now, doesn't really go into too much detail about the algorithms, and there's a bit more detail in a second, but just to give people a flavour if they haven't got any familiarity at all. So broadly, the way these algorithms get high order accuracy is that they represent the function, the underlying flow solution, using high order polynomials. So if this grey line is some schematic illustration in 1D of the flow solution, a traditional low order finite volume solver, which is the sort of bread and butter of industry tools, would chop up this domain into separate little finite volumes and represent the solution within each finite volume with a piecewise constant approximation of the data, which gives you some reasonable approximation of the underlying grey function. What flux reconstruction schemes do, like a range of other similar methods, I've mentioned discontinuous Galerkin, is that they chop up the domain into bigger elements. So there's 3 big elements here. And then within each of those elements, they create a polynomial fit of the data. And you can see in this particular case, we've got polynomials that fit through certain points of the data. It's like a collocation projection of the data onto a polynomial basis, or fit with Lagrange polynomials. Going into a little bit more detail about exactly how the methods work, just for 5 minutes. And so I can just introduce some of their other characteristics. If you consider each one of these arbitrary elements, from a computational perspective, you map it onto a reference element between -1 and 1. You deal with the mapping separately. And in the context of one of these mapped elements, we're representing the solution, as I've pointed out, with a summation of Lagrange polynomials. So it's this polynomials that go through values of the solution at certain so-called solution points inside each element. And this is of degree k in this case. In fact, here specifically k equals 2. Then in order to, I'm just going to walk you through the steps of how the flux reconstruction process actually updates this solution polynomial in time. So it builds something called a discontinuous flux, which is also of degree k, and it's a representation of the flux in the element. So basically you evaluate the flux of the solution at each solution point and get these values, and then with the same Lagrange basis create this polynomial representation of degree k of the flux. That's called the discontinuous flux. And you do that in the adjoining elements as well. In general, this is discontinuous between elements because I should have made this clear. These solution polynomials, as you'll see in my schematic, are allowed in general to be discontinuous between the elements. There's no explicit continuity of the solution enforced. So we have our discontinuous flux. We then go back to our solution, and the solution has these pairs of values at interfaces because it's discontinuous. And from these, we can use technology from a finite volume community to work out a common value of an interface flux, so a Riemann solver. For example, you plug in a left and right-hand solution state and you get a common flux value. So we're now in this position of having a discontinuous flux inside each element and common interface fluxes at the boundaries. And then we introduce, and this is the sort of key core of the flux reconstruction approach, the concept of a correction function. So we have to start with a left correction function, GL, that has a value of 1 here on the left, 0 here on the right. It's of 1 degree higher than the solution polynomial. So here it's a 3rd order polynomial because the solution was 2nd order. And we scale this correction function by the value of the jump between the common interface flux and the discontinuous flux at the left-hand boundary. So we scale the green line by this jump, like this, and then we add this scale correction function onto the discontinuous flux, and it now attains the value of the common interface flux at the left-hand side. And has added the wiggles of the polynomial onto it. And then we do the same from the right. So we have a right correction function that's a mirror image. We scale it by this jump, add it on. Because the correction functions are 0 at their sort of opposite ends, This one then didn't move that point here. So now you have this corrected flux, and we can do this in all of the elements. So you have a degree, because you've added a degree k plus 1 polynomial to a degree k polynomial, you have a degree k plus 1 corrected flux that's C0 continuous between the elements. And it's this corrected flux that you can evaluate the gradient of, so in general the divergence of, at each solution point, and use this via a suitable temporal discretization of this semi-discrete form to update the solution in time to the next time level. Not going to have any more about the numerics here. I'm just going to move on to the sort of computing part. But the reason it's in here, I realise there's more of a sort of supercomputing theme to the talk, but the reason it's in here is just I think it's important to give a flavour of the algorithm, because it contextualises some of the nice performance numbers in terms of percent of theoretical peak that I'll show in a minute. Because and the reason we get those nice performance numbers is because you have this very high compute intensity of doing structured operations on these polynomials inside each element. So it's just a sort of flavour of how the algorithm, the nature of the algorithm is important in the context of the hardware to get a good flop number. By changing the form of these green correction functions I had within this flux reconstruction framework, you can recover a whole range of different numerical schemes, some existing and some new ones, and we've done a lot of work in identifying new schemes, looking at their stability for linear problems. This was work I did with Tony Jameson at Stanford back in 2011, and have continued at Imperial College looking at properties for nonlinear problems. And this is what I just mentioned, which is as well as these algorithms being fundamentally a good fit for the problem space in terms of their accuracy and their ability to work on unstructured grids, also because of their nature, and that's detailed here, they're a very good fit for these modern hardware platforms in terms of being able to leverage an abundance of flops that comes from parallelism. Okay, so that's modern hardware and the algorithms. I now want to move on to PyFR. So PyFR is our software, which is an implementation of flux reconstruction algorithms, hence the FR in Python, hence the PY, so PyFR. That's our logo. These are our current feature set, compressible and incompressible Navier-Stokes. It started as a compressible solver, we just added incompressible recently. Mixed element unstructured grids. Explicit in time, although it does have implicit solvers via dual time stepping, we've added recently. Single and double precision, a range of open input and output formats. And then critically, this last part is it has the ability to run across a range of hardware platforms, all from a single code base, a single implementation. So with our single 9,000 lines of Python, we have a 3D mixed element unstructured grid, high order accurate, compressible and incompressible Navier-Stokes solver that can run across clusters of standard CPUs, clusters of Intel Xeon Phis, KNLs as well are not on here, NVIDIA GPUs, AMD GPUs, and systems with heterogeneous mixtures of all of these. We've published some papers on running on mixes of AMD, Intel and NVIDIA hardware from a single code base. So I'm going to talk about how we've done this primarily, because there's quite a lot of innovation in here, because this is a really hard, if anyone's tried to write a code base that runs across multiple platforms. And there's more and more pieces of technology coming along to help, but to do it in a performance manner is still difficult. So we have a Python outer layer. It's like the sort of glue that glues everything together. And this builds various operator matrices that we need at the beginning of a simulation. It manages the hardware specific data layout. So you need different data layouts for different platforms to be optimal on different platforms. It manages that. And it manages the generation of hardware specific kernels. I'll talk about what I mean by hardware specific kernels in a second, but basically it's as it sounds. So the compute intensive parts of the code designed bespoke for the hardware platform that you want to run on. It manages their generation. Just to give a quick look ahead, we use a runtime code generation paradigm, where the Python generates low-level code at runtime for the particular hardware platform. And then it also manages the MPI layer. So back to these hardware-specific kernels. Well, you can identify when you look at Flux reconstruction, there's two types of kernel that you require. One is matrix multiplies. That's here. And this is relatively straightforward to go cross-platform with, at least in the naive sense, right? Because you've got cuBLAS for NVIDIA, CLBLAS for AMD hardware, lots of BLAS libraries for CPUs. So you can just pick your favorite linear algebra subroutine library and, what's the word I'm looking for? You can rely on that to do your matrix multiplies. There's an aside I'll take in a second about how we've gone just beyond using that, but that's what we can do as a baseline. This bit's more difficult, right? Because these, what we call pointwise kernels, these contain the more esoteric, domain-specific functions we need for a flux reconstruction solver, like these Riemann solvers and flux functions, etc. So the way we take that cross-platform is we use something called Mako. So Mako is a Python-based infrastructure for templating the construction of HTML for websites that we have tweaked slightly to template the construction of low-level kernels in C with OpenMP or CUDA or OpenCL. So you write your algorithmic specification once in this Mako, and you can embed Python in it, and it's all language. I'll show you some examples in a second. And then at runtime, this is interpreted, if you like, by PyFR. The bit that deals with this is all included in the 9,000 lines of code, by the way. This isn't a separate piece. And then it will generate low-level code that's compiled, linked, and loaded at runtime, and then can be called by this outer Python layer. So the Python invokes these kernels, but it also generates them at runtime. It manages to data layout for the kernels, invokes the kernels, and generates the kernels from the Python. But the code that's actually running is C or CUDA under the hood. The overhead from having Python control it is like 0.1% if you benchmark. So there's some people are surprised when you say you've got 13 petaflops on 18,000 GPUs with a real-world simulation using a Python code. And we're not tricking anyone, it's all here, right? But you're using the Python to generate the code, the low-level code. This is how you get that performance. And one more point here quickly is you now have this nice orthogonality, which is what you're looking for, between the algorithm and the hardware platform. So if I add a new Riemann solver, it's instantly, in our templating language, it's instantly across all of the back ends. And if I add a new back end, new piece of hardware, I just have to go in at this level, and you instantly get access to all of the mathematical functionality you had before. So it's an important orthogonality to have. Because one strategy for this is to have separate implementations of each function in different languages and promise yourself at the beginning that you're going to maintain them all with the same feature parity. But that's a terrible approach because you never do. I went through various iterations of this. This is an example just of this Mako because it's a slightly longer talk, so I had a little bit of time to go into some details. This is an example on the left of a Flux, Euler and VINCENT Flux kernel written in this Mako language that we have. This is code from PyFR. Over here, this is CUDA that's generated, and it goes down the screen, because there's lots more of it. Just want to make 3 points quickly. One, as well as generating CUDA per se, there's three other points. As well as just generating the code, there's 3 other points I want to make. One is that the templating layer abstracts the data layout. So you'll just notice here we have this quantity inv row, which is 1 over the density, is defined as 1 over S0. S is your solution state matrix, the 0th entry is the density. That sort of makes sense, even if you don't know the details. But that's just 0. In the context of these kernels, which work at a specific solution point, it's just that 0 index means the first entry of your solution state. Over here, you'll see what's generated under the hood is this great big horrible thing showing we've got AOSOA data formats under the hood of the CUDA backend for where to actually access that in memory for the CUDA implementation. So we abstract the data layout. We have access to, and we can template based upon, a whole bunch of runtime parameters, such as the dimensionality of the simulation, 2D or 3D. So this kernel is written generically for 2D and 3D. Here, there's a 2 there, so it's because I've generated a 2D Euler Flux kernel in this case, all done contextually at runtime for the simulation you want to perform. And taking that templating further, Via Mako, you have access to for and if statements and some other statements, and within that, you can basically use all of Python to do as if, else, and all of Python basically to do your templating, to generalize these templates for multiple dimensions, for example. So I guess it's probably a good point just to say I'm not, well, shall I make this point? Now I'll make it quickly. So, and this works, right? And we've had a lot of success with this. I'm not advocating that this is the approach that everyone should take. It is purposefully our implementation is purposefully domain specific to us. So this Mako layer can only generate the type of kernels we need to do flux reconstruction. It's not something you could necessarily take and use over a whole wide set of domain spaces. But that was a strategic decision at the beginning, right? Because if you try and have one of these things for doing every function in the world, well, then the performance is very hard to get. If you have it for doing the most minutiae of specific things, it's not useful to anyone. We tried to get a balance there. There's obviously technologies for trying to do this cross-platform more generically that people are exploring and have become more and more sort of prevalent. If any of them ever took off, we could just basically tear out this bit of PyFR and put them in there under the hood. And this is, I said I'd come back to this. I said this path was easy because you can just use dgem or sgem from Black. Yeah.
So what you're saying that if, for example, for molecular dynamics, if I would like to use this kind of framework, I would have to develop a PyMD with generating this writing this 9,000 line Python to have the Mako that would fit the kind of algorithm I need in MD.
If you wanted to follow this exact paradigm for a different domain space, then depending on what the domain space is, you could reuse a whole bunch of this. But it would be very domain specific as to whether you could reuse this or had to do it yourself. Fundamentally, though, in a different domain space, this concept absolutely would work. The concept of templating, I think, the concept of templating with Mako to generate low-level kernels would work. But I guess the point I want to make is there is no easy solution to this problem. Here, dgem or sgem from BLAS, you can do more than that with generally. So about the matrix multiply. So we do a lot of this, C equals A times B, where C is, it sounds a bit rude, it's short, fat and dense, but basically these are called block by panel matrix multipliers, right? So A is relatively small and square, of order by 100 by 100, that's like the flux reconstruction operator. B is the solution state, so it's a great big dense block of numbers, and that will produce, B is the solution state, great big dense block of numbers, it will produce C, great big dense block of numbers. The key is this, and this A matrix is, as I said, relatively small and square, but it's known a priori, and its entries never change. And it can actually have quite a lot of structure to it, including in some cases quite a lot of sparsity, but not always. It depends on the nature of the flux reconstruction algorithm that you're using. The point is, that gem in dgem, the G stands for generic. So you don't need to apply a generic matrix multiply operation here. You can leverage the fact you know what A is. And you can generate, at runtime, a function called multiply by A that you pass B and it gives you C. And embedded in this function are all the entries of A, expanded in a particular way that make that multiply by A as efficient as possible, leveraging all of the specificity that you know about A. Yes, sure.
What is the size of those matrices?
A is of order 100 by 100.
Right, so
But they vary depending on the polynomial order of your scheme. So they can go from maybe 5 by 5 all the way through to 150 by 150, roughly.
So basically your matrix multiply code is completely unrolled, like you have the
Yep.
coefficients already.
You unroll all the coefficients in the kernel. Okay, you can get even more clever if you want to, and you can unroll parts of it, and then if there's little blocks of dense parts, you can put them into another library, and there's this libxssm library from Intel for doing extra small matrix multiplies And so I should say this technology here for doing this is all in a code called Gimmick that's also open source. Gimmick is now a dependency. Gimmick is now a dependency of PyFR. I've got that the right way around. PyFR depends on Gimmick for doing this. If you want to do this, there's a journal paper we have published on this with colleagues in the Department of Computing at Imperial College, with whom we developed the technology. It runs cross-platform as well to support the cross-platform paradigm of PyFR. And for the KNL part and the CPU part, there are various interactions developing with Intel in terms of this lib. Is it libxSSM or libxXSM? Libx. There must be an S for small. Okay, double M. Right. Anyway, I'll get that. Right. Thank you. Anyway, you can optionally turn that on and off in there, and there's all sorts of games you can play. We're just sort of fun if you're that way inclined, but sometimes anyway. So right. What that means is, from our 9,000 lines of Python code, you can run on a Raspberry Pi all the way through to this laptop driving the PowerPoint presentation, through to a heterogeneous system under someone's desk with NVIDIA, AMD and Intel hardware in, through to all of Titan without changing anything, which is quite cool. 9,000 lines of code, slightly outdated now because we added in the incompressible solver, so there's about 10,000 lines of code, but anyway. Leverage the Python ecosystem heavily to keep the number of lines of code down. It's all open source. I'm a big advocate of open source software for scientific computing. And you can download the code from here and here and follow us on Twitter. Okay. So, I've talked about the algorithms. I've talked about the hardware, the algorithms, our implementation. So now I want to go back to this problem space of green aviation, and in particular low pressure turbine simulations that was my sort of motivator at the beginning. So this is a plane. This is the engine, for those of you who aren't so familiar. At the back there's something called the low pressure turbine, right at the back. The role of the turbine stages at the back are to extract energy from the exhaust gases to spin a shaft in the middle to power parts up the front. So that it needs to be as aerodynamically efficient as possible. It's like a wind turbine, right, on a hill somewhere, but except in a jet engine to extract energy from the exiting flow. It needs to be as aerodynamically efficient as possible, also as lightweight as possible, which means to have as fewer of these. If we zoom in, see it's got all these blades. This is what the air goes over to make it spin around. You need as few of these as possible to make it as light as possible. And there's a sort of optimization there between number of blades and aerodynamic efficiency. If you want to do that optimization effectively on a computer, you need to be able to simulate the flow accurately, and that's where all of this technology comes in. So we have been doing a bunch of these low pressure turbine blade simulations. All have these funny different sort of codes associated with them. These first ones are T106D, Reynolds 80,000, Mach 0.4. So it's compressible flow. We've been running on two systems. PISDATE, which is at the Swiss National Supercomputing Centre, has a 5,000, well at the time K20Xs, but now it has 5,000 P100s. And on Titan, which is at Oak Ridge, which has 18,000 K20X GPUs. This is sort of, it doesn't need to be in there necessarily. We've been using different versions of PyFR now, but these results are done with a specific version. Some numerical comments about we're using an explicit time-stepping scheme run in double precision, and we use something called anti-aliasing to help stabilize these simulations of turbulent flow, which is a numerical procedure I won't go into the details of now. First, I want to present some scaling results for this problem. And first of all, weak scaling with fourth order solution polynomials inside each element. So weak scaling is where you keep you increase the problem size proportional to the number of GPUs in this case. So we increase the problem size from 1 blade through 5 blades and run on proportionally more GPUs each time. And if you've got perfect weak scaling, you'd expect your runtime to stay constant. Okay, this is weak scaling. And this is our weak scaling results on both Titan and PISDATE. The red line is ideal, the blue dots are PyFR. So we get completely perfect weak scaling on both of these systems, all the way up to 15,000 GPUs on Titan. My comment about this, because it all looks like, you know, there's like 9 dots on there and we can just skip on. There's a lot of... These algorithms should allow you to do this, and clearly they do because we have. But there's a lot of mistakes you can make along the way in the implementation which will mean you don't get this type of weak scaling. So it's a reflection of the quality with which the software has been implemented, which is nice to see this. I was going to make another point, but I've forgotten. Anyway, so we get very good weak scaling. Sustaining approximately 50% of theoretical double precision flop peak. Right, so I've shown 50% to some people and they go, oh dear, there's lots of room for improvement there then. And you're like, well, this is slightly frustrating if you know anything about the domain space. So a finite volume solver will get maximum 2 or 3% of theoretical peak on these modern hardware platforms. This is the theoretical peak number. The theoretical peak is calculated, I mean, you'd have to be doing some crazy stuff to ever get it. So this, for a real solver that's running, is really nice. These numbers are of the GPU peak performance. We don't, on Titan for these runs, we weren't running on or counting the potential performance of the CPU component. So yeah, that's a good point to be clear.
In general, when you use the GPU, you only use the GPU or do you also use
we could do, because we can do this heterogeneous computing, but in this case we didn't. We just elected to use the GPU because there's just so much more performance there than the CPUs. And there's obviously an overhead of having to partition in a... Partitioning is an interest, we have this paper on this, but partitioning an unstructured grid for a heterogeneous system is not a solved problem, we came to realize, because the ratio of, maybe people are giving talks on this today, I don't know, but the performance ratio of the different element types is different on the different platforms. And it's like this non-linear sort of horribleness. So this was just on the GPUs. Yeah. Sorry.
In order to determine the peak performance, so this is straightforward. So kind of number of cycles times number of operations per cycle, right?
Yeah.
You then take into account that, for example, you can do multiply add, but you don't have balance multiplies and adds and stuff like that.
So the maybe I don't know enough detail to. So the performance, the theoretical peak numbers are obtained. So the first thing to note is that like 90% at these levels of polynomial order P4, 90% of the operations are just from the matrix multiplies. So we estimate as an upper bound, or conservative bound I should put it, of the number of operations you'll need to perform just based on how many separate multiplies and adds you'll need to do that matrix multiply. If under the hood something different is done by Kublas, we don't make ourselves aware of that. But there's a fundamental, you can put a fundamental limit on how many are going to be performed to do a matrix multiply. And then for the pointwise kernels, which constitute about 5 to 10% of the time, we count the floating point operations. Now that's reliant on us, like as per what the unrolled maker into CUDA looks like. That's reliant on us having not written stupid code, right? Because if we wrote stupid code with loads of excess number of operations in it, we'd be counting excess operations to get an artificially inflated flop number. So that is too important. It's hand counting basically of operations. And then when you know that and you know the time, wall clock time per time step, and you know the operations per time step, we work it out.
Have you done something similar for the memory bandwidth? So how much of the memory bandwidth here?
We, not in these runs, but we have this paper in Computers and Fluids on the heterogeneous computing performance. And in that we go into bandwidth as well as flops, and I can send you that if you want to, but not for this work. Yeah.
You have some communication between GPU?
Yes, so that was a point I was going to make here. So the reason you can get this is because we overlap into GPU communication with useful GPU local work. So the algorithms allow you to do some things on the GPU while the MPI data is in flight. There's local stuff to be done. So the first thing you do is put the data at the boundaries of the MPI rank, send it in flight between them, then go back to that rank and do completely local things that don't rely on its partner's data of having arrived. So yeah, the overlap of communication and computation is how you get this. That was the point I wanted to make but forgot, so thank you. Okay, I'll keep moving on, but happy to do keep interrupting if you have questions. Then strong scaling. So strong scaling, we tested on a small section of one of the blades, just as a demonstrator. So this is again on Pisdane and Titan. Strong scaling is obviously a fixed problem size over more and more GPUs, and you expect the speed up to be proportional to the number of GPUs. This is ideal. This is what we get with PyFR. So you can see it does start to tail off. Just want to contextualize this tail off with a few numbers. So we start down here, around 50% of peak, approximately fully loading the GPUs. Then we start splitting it down over more and more GPUs. Up here, we reduce to about 40% of theoretical peak. Obviously, it'll just get worse as you keep going. But to understand why you're starting to see this significant drop-off, you can see in both these cases we're now of order 1 element per CUDA core, because you're adding more and more GPUs to a fixed problem size. And the parallelism, in terms of how the algorithm is written, exploits parallelism down to that level. So once you get beyond that, you're just fundamentally, you've run out of stuff to do with the hardware. So we tail off eventually, as everyone should do, but we tail off at the right time in terms of understanding what's happening. Okay, so scaling. Sustained peak performance. These results all underpinned our entry to the Gordon Bell Prize last year, which we got shortlisted as a finalist. We didn't win, unfortunately, but we had fun along the way. So one of the things Gordon Bell Prize is interested in, is, as well as scaling and doing something useful, is sort of what's the biggest run you can do. So we fired up the entire 5-blade cascade, P5, and the whole mesh at nearly 200 billion degrees of freedom, and that ran on 18,000 GPUs and sustained this 13.7 petaflops double precision number at 58% of theoretical peak with our little Python code. So you can view this in different ways, right? And in fact, what the Gordon Bell Prize effort and entry and process made us do was to really stress test the technology on an extreme scale. And you'll see at the end of my talk, we've stepped back a bit from 18,000 GPUs to 5,000. And now doing anything on 5,000 seems relatively easy. And we're actually doing some real simulations in collaboration with an aerospace company on those scale of problems. So it's sort of something that pushes your boundaries. You have to develop a whole bunch of technology along the way. I'll talk a little bit about it as we go into the application stuff. But to do these runs, it's not just about the solver and it's not just a fancy algorithm. It's all like a data I/O. Everything has to be done right, okay, for these types of simulation at this scale to run. The Gordon Bell Prize effort and going to this scale of problem forces you to do that. And then we did a physics run. So this is where we actually gathered data. It's all of the blades, now with 4th order solution polynomials, so 113 billion degrees of freedom on 5,000 GPUs of Titan. We ran for 35 hours, which gives you 5 flow passes over each blade. So here's the blades lined up. This is so the flow's coming in from the top. It's turned around the blades. It separates here, transitions to turbulence. You've got a turbulent wake behind each of the blades. Also picking up, you can't really see it very well here, but this acoustic sort of wave phenomenon. That's a 2D slice. This is 3D, right? We've rotated it around looking at the wake behind one of the blades. Go back, sorry. I messed up my lovely animations by clicking too quickly. There we go. This is a wake behind one of the blades. This is a good point to interject with another quick aside about some technology we had to develop, right? Each frame, this animation's got hundreds of frames. And each frame requires processing of a couple of terabytes of data, right? So how do you make the animation? Because writing terabytes of data to disk, loading it up in ParaView, basically each frame by hand would take about a day to make. So the way we made these animations is we developed a whole in situ visualization stack in collaboration with ParaView and NVIDIA that plugs into PyFR. And you've got the solution state in the GPU memory live as it's running. And then live as it's running, it takes that data, processes it with whichever filters you need to make this, does all of the rendering, and basically spits out a PNG image that's a few megabytes per rank and writes it to disk. It composites them together, obviously, across all of the ranks and writes them to disk. So we're further developing this at the moment to have it so it works. We've done it on a smaller problem, but not on a problem of this scale. Works live So you can fire up ParaView and look at a simulation as it's running and zoom in on pieces. And so this in situ visual, generally in situ analysis, in situ being in memory as it's running. These paradigms are super important if we're going to perform useful simulations at this scale. It's not just the solver technology, there's these other auxiliary bits that fit around it. Because you can't write this data to disk, and even if you, because it's so big, efficiently. And even if you did, you're never realistically going to open it up again and look at it. So you have to extract stuff as you go along. And to some people, this can seem a bit unpalatable, because you're expending all of this effort to simulate something where you could capture and store every single thing. And I'm telling you, you should chuck lots of it away for practical reasons. But you need to now, because you just can't deal with the data. It's a big data problem. So this is an interesting space we're moving into. So what would be useful in this context is something that can automatically tell you on the fly which important bits you want to extract and not. And so there's a machine learning piece in here we're looking at exploring at the moment. And so you can position different cameras, in this case a priori, position cameras zoomed in on different regions of the flow. And we're doing a direct numerical simulation, so you capture all of these turbulent scales with our 113 billion degrees of freedom. And is there one more? Maybe there's one more. No, we're done. So there's some nice videos. What's also obviously very important is a quantification of the results. There's one such quantification here, although we're looking at doing others for another problem I'll talk about in a second. This is isentropic Mach number. And these red points are from experiments. This is basically like the pressure distribution along the front side and the back side of the blade. And this is the result from PyFR. So we get this very good agreement, including in this region where the flow separates and becomes turbulent. There's a slight disagreement on the leading edge, but apparently this is really sensitive to experimental error in the inflow angle. And so they let us off here. So we're getting, what's the time? Right, so nearly had my hour. So those results were from the Gordon Bell Prize entries I've alluded to. What we're doing now is taking these forwards in collaboration with MTU Aero Engines, a German company who design low-pressure turbine blades, in the context of a different blade configuration called the MTU T161 at 2 Reynolds numbers, a slightly higher Mach number. We have an Insight Award for 200 million GPU core hours on Titan at Oak Ridge this year and next year. There's no animations here, they're just static, but we're doing these 2 Reynolds numbers. The full blade at full span with end walls, and this particular configuration has end walls that are expanding, and there's lots of interesting physics there. You can see, so these simulations have actually higher resolution per blade than our previous simulations. So this has 56 billion degrees of freedom per blade. You can see all of the scales that we're resolving. You can zoom in and into these images. As indeed the slide does, that was convenient. So you can see all of these structures. These simulations are literally running at the moment, hopefully, unless they've crashed in the last half an hour while I've been giving the talk, because, anyway. This is another image of the underside of the blade, and in this particular case, you get transition to turbulence on the underside of the blade, and all of these structures we're resolving. So, that's my time pretty much up. So I've talked about basically the technology underpinning a set of high fidelity simulations of turbulent flow over low pressure turbine blades at unprecedented scale. I've talked about weak and strong scaling and peak performance in the context of these simulations. I've explained how we've got good agreement with the experimental data. We've done all of this with now about 10,000 lines of Python code that can run cross-platform. And this is just sort of one other thing that I had left, just to contextualize where we're at in terms of, in the CFD community, there's a report that NASA published 2 years ago now called CFD Vision 2030, which is the roadmap towards 2030 for the computational fluid dynamics community. And there's lots of milestones on here, and I tried to put on here roughly where I thought our technology was. Luckily, the PyFR logo's got like a 5-year window on it, so it's not too precise. But in particular, with this in situ this part's called knowledge extraction. The in-situ vis technology, we're definitely pushing into where the Vision 2030 report believes we're supposed to be not until about 2025. So that technology, I think, we're quite excited about and looking to push further. This is the team of people that underpin everything. I just come and give the talk about it. These are the people that do it. Some of these have moved on to various other positions around the world now. Some of them are still with me. I should absolutely thank the people who've given us access to their supercomputers, and in particular the guys at the Swiss National Supercomputing Centre and Titan, the guys at Oak Ridge for Titan, because they've been incredibly supportive of what we've done, and the people who funded the research. And I'll leave it there. So that's it. Thank you.